Hello and welcome to our next lecture on linear block codes. Let's start with a brief outline for today's talk. We will today study Hamming codes followed by low density parity check LDPC codes. Then we will look at the notion of optimal codes and finally maximal distance separable codes, also called as MDS codes. We will top it up with some examples. So, that is the brief outline for today's talk. Let us quickly recap what we learnt in the previous lectures. We have already considered the probability of error P error for any decoding scheme as that probability which the decoder output is a wrong code word. This is also called as the residual error rate, which means that despite applying the error control coding technique, you still have a finite non-zero residual error rate. We also found that the upper bound on the probability of error Pm can be expressed as follows, where capital M is 2 raised to power k, k being the length of the information word. D star happens to be the minimum distance of the code, and this is over a binary symmetric channel. So, small p is the probability of a bit getting flipped. So, we found this up using a union bound. We also found out what do we mean by the term coding gain. It helps us compare two systems. So, if you have, for example, a coded and an uncoded system, and on the y axis we have the probability of error, on the x axis we have EB over N naught, which is a measure of the signal to noise ratio in terms of dB. For a certain probability of error, say in this case approximately 10 raised to the minus 5, we can say that the coding gain is this decrease in terms of EB over N naught. That is, what is the reduced SNR required to give you the same performance in terms of the bit error rate. But finally, we can sell a system in the market if it adheres to certain probability of error, and this axis changes depending on the application. So, if you have a medical data imaging problem, I would rather be around 10 raised to the minus 6 or 10 raised to the minus 7, whereas if I am just doing simple digital voice transfer, 10 raised to the minus 4 and 10 raised to the minus 5 are good enough. So, this axis actually tells you what is the application level and the quality of service that goes with that application. So, coding gain changes with the PE. Coding gain is measured in dB, and typically it increases as PE decreases. The limiting value as PE tends to 0 is called the asymptotic coding gain, that is the theoretical upper limit. We also looked at the Hamming bound or the sphere packing bound, and if you look at the binary case, the Hamming bound is given by this following expression, where n is the block length, k is the length of the information word, and t is the number of errors that it can correct. Now, we also made an observation that just because we have a set of integers n, m and t which satisfies the Hamming bound, it does not necessarily mean that you can find a linear block code that exists for those numbers. And you can alternately write the Hamming bound by substituting m is equal to q raised to the power k as follows. So, please remember the Hamming bound is for a query code, it is not necessarily for binary. Binary is a special case when q is equal to 2. What is a perfect code? Well, a perfect code is one that achieves the Hamming bound, and we have put that equality here, and this is the condition for a perfect code. Now, we will move on to a class of codes called Hamming codes. The property of Hamming codes is as follows: the n comma k is given by 2 raised to the m minus 1 comma 2 raised to the m minus 1 minus m, where m is any positive integer. So, all Hamming codes satisfy this n comma k condition. So, let us say m is equal to 3, and substituting 3 here would give you 7, and substituting 3 here will give you 4. So, 7 comma 4 is a valid Hamming code. Alright. So, if you put m is equal to 4, you can have another value, say 15 here and 11 here. So, 15 comma 11 is another valid Hamming code. So, let us look at the generator matrix for a binary 7 comma 4 Hamming code. So, we have the number of rows as 4 because clearly k is equal to 4, and number of columns is 7 because n is equal to 7. So, it is a k cross n matrix which is the generator matrix. It forms the basis that generates the entire code space. Now, you can always find the corresponding parity check matrix. In this case, we list out the parity check matrix. Again, please note that the dimension is n minus k cross n. So, n minus k is 3 because n is 7, k is 4. So, 7 minus 4 3. So, the number of rows is 3 and number of columns is 7. But we make a couple of very interesting observations. The first observation is that all the columns of H, right, are basically the non-zero vectors, the binary vectors of length 3. So, you have 0 0 1, 0 1 0, 0 1 1, so and so forth up to 1 1 1. So, all the 7 possible combination, barring the 0 0 0, there are 7 possible vectors of length 3, all of them are listed in some sequence, and this happens to be the check matrix. So, we know that you can have an equivalent parity check matrix by simply rearranging the columns. So, since I have got these 7 vectors, and of this I have to identify 1 0 0, 0 1 0 and 0 0 1 to be kept on the rightmost side, we can simply rearrange them. Okay. So, please note we need it in the systematic form, which is of the type minus p t I, and I happens to be the identity matrix which is 3 cross 3, right. So, what we want to do is simply rearrange those columns and you get your H matrix. And needless to say, this can be, this is not necessarily unique, you can have many other rearrangements for the first 4 columns and each one will be a valid H matrix. But this gives us a very nice way to put it in the systematic form. So, this is your parity check matrix for a 7 comma 4 binary Hamming code. Now, if we were to look at the generator matrix in a systematic form, we have this P transpose here for this one. Please note, in binary 1 plus 1 is 0. So, minus 1 is equal to plus 1. So, minus sign is not really making any difference, it is as well as minus p t is equal to p t. So, all you need to do is take this portion and just put a transpose of it and follow it, if precede it with an I. So, I have got this identity matrix 4 cross 4 and this is the transpose of that p t, which gives me the P matrix, and I have a quick rendering of the generator matrix in a systematic form for the binary 7 comma 4 Hamming code. This is your parity matrix and this is the I matrix. Now, we observe that no 2 columns of H are linearly dependent, right, because there are only 7 columns and we have exhausted all the 7 vectors which are non-zero to form those columns. Clearly, no 2 columns of H are linearly dependent, right. But for n greater than 1, it is possible to identify 3 columns of H which would add up to 0. So, you can always go back to your H matrix and pick up 3 columns, and these 3 columns would add up to 0. Now, we established in the last class that that could lead us to the minimum distance of the code. Let us have a quick recap on that. So, we know that any valid code word C H transpose is equal to 0, that is by construction. So, what is it doing? This is H transpose. So, C is actually picking up the columns of H, right, because this is H transpose. So, if you have this C as C1, C2, Cn multiplied with H transpose equal to 0, all it is doing is the C1 is picking up the first column, C2 is picking up the second column, and Cn is picking up the nth column, and it is adding up to 0. So, if the minimum number of columns of H which add up to 0, that is the minimum weight possible, because in a binary case these are either ones or zeros. For example, if it were 1 0 1 0 0 1 and you have got this H transpose equal to 0, then what it does is this first guy picks up the column 1 of H. So, 1 into say column 1 of H, CH1, and the 0 picks up the second column, multiplies it by 0. So, it is negated, plus 1 times CH3 picks up the third column. So, it picks up the first column, third column, and nth column. Right, and that is 0. So, essentially the number of non-zero elements, in fact here in our binary case the number of ones here is picking up one column each, and that is adding up to the 0 vector. So, the minimum number of columns of H that add up to 0 would give you D star, because how many columns they are picked up by the non-zero elements of this code word, and therefore, that directly corresponds to your D star. So, we come back to our slide and have a look at the H matrix here, and we see that you can pick 3 of those columns and you can ensure that they add up to 0. Any 2 are linearly independent, but 3 of them add up to 0. It tells us that the minimum weight of this Hamming n comma k Hamming code is equal to 0, but we have already seen that for distance D star equal to 3, it can at best be a single error correcting code, because D star should be greater than or equal to 2t plus 1. So, you have these Hamming codes, even though they are perfect codes, because they satisfy the conditions for the perfect codes, are only single error correcting codes. Nonetheless, they are very good, they are optimal in certain senses. So, 7,4 Hamming code is not only a good textbook example, but can also be used to give you a single error correction. Now, for perfect codes we need to check this condition, because this inequality should be met here. So, if it needs to be equal if it is for perfect code. So, we put this equality. So, 2 raised by k up to t error correction should be equal to 2 raised by n, but in our Hamming code case we know the 7,4 code, n is 7, k is 4, t is 1. So, if we put this condition, k is 4, n is 7 and t is 1. So, we only take the first 2 terms in the summation and substitute them. We quickly can verify that indeed this equality holds, and 7,4 Hamming code is a perfect code. Now, let us see what we can do by tweaking it a little bit. So, already you know you have an n comma k Hamming code, you can always modify it to an n plus 1 comma k code with d star is equal to 4. So, by just adding one more bit to the code word, you can, so adding, what do you mean by adding one more bit? I add a parity bit and I make it n plus 1 comma k code, and suddenly my d star becomes 4. We can go the other way also, and we can shorten the n comma k code. Now, how do we do that? Well, n comma k also gives us the idea that G is k cross n. So, I can start deleting rows and columns. So, if I can delete L rows and L columns, I get a modified shortened G matrix for a Hamming code, right. So, you can also remove the columns of H and you will get the equivalent H. So, I can play these small tricks to get a smaller or a larger code with interesting distance properties. There is also an alternate definition of Hamming code. So, let n is equal to q raised to power k minus 1 divided by q minus 1. So, you can have q, for example, for binary case q is equal to 2 and k is equal to 4. So, you can substitute these values. Then an n comma k Hamming code over GFQ is a code for which the parity check matrix has columns that are pairwise linearly independent. Okay. So, we are now trying to tell you in a kind of a different way how you can actually construct a Hamming code. We have to get the pairwise linearly independent columns of H, and once we have an H, we can always construct a G and vice versa. So, that is, the columns are a maximal set of pairwise linearly independent vectors. Okay. And we saw the simple example for a 7,4 code, that each of the columns were pairwise linearly independent, but 3 of them added up to 0. We now look at another class of codes, another class of linear block codes called the low density parity check code. But for that we start with a slightly different definition, which is the Gallagher code. So, an R comma S Gallagher code is a linear code with a check matrix H which satisfies the following condition. So, H matrix has every column has R ones and every row has S ones, rest are all zeros. So, suddenly if you want to visualize a binary code, we are putting constraints on how many ones you can have on every column and how many ones you can have in every rows. And if we make this constraint strict, that is R and S values are small, then my H matrix is pretty much full of zeros. Okay. So, if a Gallagher code with small values of R and S is basically a parity check matrix which is mostly zeros and a few ones in the rows and columns as dictated by R and S, and by squeezing R and S I can reduce the number of ones and thereby making it a low density. Low density of what? Ones. So, it is a low density parity check code, and we will quickly come to the benefit of this, but first let us understand the job of a parity check code. What a parity check code does is it takes the receipt vector nu H transpose, it checks for the syndrome. Now, each time I do nu H transpose, the different elements of nu takes up the rows, the columns of the H matrix and performs computation. But if most of the elements are 0, then the computational load really goes down. So, question is, can we still have good interesting distance properties despite having the parity check matrix highly rare, that is the density is pretty low. So, thus an LDPC code has a sparse parity check matrix with very few ones in each row and column. So, typically LDPC code has R less than or equal to log to the base 2n, where n is the block length. So, if you remember, the size of the parity check matrix is n minus k cross n. There are n columns and number of rows and number of ones in every column is limited by log to the base 2n. So, it is kind of a rule of thumb which gives you what is low enough. So, this code can be written as n, which is the block length, R where every column has R ones, S where every row has S ones. So, n comma R comma S LDPC codes. These are the parameters of my LDPC codes. Let us quickly look at an example. So, let us look at a H matrix, which is the parity check matrix. Let us first look at the columns. Pick any column, say the third column. I see only 2 ones. I pick any other one, suppose I pick up the fifth, again I see only 2 ones. I pick up any one and again I see only 2 ones. In fact, I can do this exercise and I can make a sanity check and see that all the columns have at most 2. So, R is equal to 2. Now, I look at the rows. I count the number of ones 1, 2, 3, 4. So, 4 ones, most are zeros, again 1, 2, 3, 4, 4 ones, 4 ones, 4 ones. So, we say that there are at most 4 ones, in fact exactly 4 ones in every row and 2 ones in every column. So, R is equal to 2 and S is equal to 4 for this parity check matrix, and if I count the number of columns 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So, n is equal to 10. Okay. So, this is 10 comma, so R is 2 comma 4, 10 comma 2 comma 4 LDPC code. So, we just now verified that R is equal to 2 ones in each column and S is equal to 4 ones in each rows, and clearly we cannot have any more independent columns in this 5 cross 10 matrix, because all possible combinations of choosing 2 ones out of the 5 possible locations, 5 choose 2 which is 10, has been exhausted. Therefore, you have n is equal to 10 and k is equal to 5, because the dimension of a parity check matrix is n minus k cross n. So, we also observe that the last 3 columns add up to the 0 vector. So, if you go back and if you look at these things 0 0 0, this 1 plus 1 0, 1 plus 1 0, 0 0. So, the last 3 columns, if you add them up, it is 0, and you can try as much as you want to, you cannot find 2 columns adding up to 0. So, the minimum number of columns that add up to 0 is 3. Consequently, the D star must be 3, and hence it is a single error correcting code. So, what does it tell us? It tells us that this is a sparse matrix. For whatever reason, let us believe that it is sparse enough, although real LDPC codes have pretty much most of the weight as zeros and very few ones. So, this is a toy example, but you will see that despite having lots of zeros, you have not compromised on the distance. The minimum distance is 3 and still it is a useful code, it can correct a single error in the code. So, this is a 10 comma 2 comma 4 LDPC code. This is an example of that. Some more definitions: an LDPC code with fixed R and S is called a regular LDPC code. So, the example that we looked at just now, R was fixed at 2 and S was fixed at 4. So, it was a regular LDPC code. But if the number of ones in the columns and number of ones in the rows are approximately R and S, So, we do not restrict it that it necessarily has to be 2, it can be between 2 and 3 and S can be between 4 and 6, we can put those constraints and then it is called an LDPC code which is irregular. So, LDPC codes can be constructed by using either a random construction or an algebraic construction or a combination of two. So, I can choose any of these techniques or combine them to form my LDPC codes. But whenever I construct an LDPC code, I first get the H matrix and then I get my G matrix. So, a simple algo is given as follows. For random construction of LDPC codes, there are 4 steps in this algorithm. Set I is equal to 1 and the second step, generate a random binary vector of length n r over s. These are the parameters, n is the block length, r is the number of ones in the columns, s is the number of ones in the rows, and a Hamming weight r. So, this is the ith column of H. So, I am constructing H, I need to get n vectors in place and I get the ith column, the ith vector as follows in a random fashion. If the weight of each row, so I put the column in place, but now I talk about the weight. If the weight of each row of H at this point is less than or equal to S, because S is the constraint I have, and the scalar product of each pair of columns is less than 1, right, then set is I is equal to I plus 1, that is I go to the next column, else go to step 2. So, we are constructing it, right, and we are ensuring that you are not exceeding the number of ones in the rows to more than S. Okay. And if you can reach I is equal to n, that is you have found all the n vectors which satisfy the conditions of the maximum number of ones in the columns and the rows, then you have actually successfully constructed the LDPC code. Now, the random algorithm does not guarantee S ones in each row, but it gives you less than or equal to S ones. Now, let us look at something called as a Tanner graph. Now, it is a very interesting graphical representation of the linear code based on check equations. So, we are again moved the focus to the parity check matrix, how it works, and since parity check matrix does the great job of either telling you whether the code is a valid code word, the received vector is a valid code word, or the syndrome associated with it, we look at the parity check matrix side. So, the Tanner graph is a bipartite graph, which means it has 2 kinds of nodes, the symbol nodes and the check nodes, and these are connected. So, each symbol node is connected only to the check nodes and each check node is connected only to the symbol nodes. An LDPC code with fixed R and S is called a regular LDPC code, as we have seen earlier. And how do we do this decoding part? Something has to be good about this LDPC code, because they are very popular, they are finding place in the newer wireless standards. One of the methods is called the bit flipping algorithm. Let us understand this algorithm and we will follow it up with an example. So, it is a simple iterative algorithm. The beauty lies in its simplicity and the minimum number of computations required to come to a right conclusion. Also, if you fail to come to a right conclusion, you can always say that sorry, I tried my best, my number of iterations have been exhausted and I could not declare the result. So, it is not that if it fails to give you a correct answer, it will definitely give you the wrong answer. It will raise its flag and say no, I could not complete the decoding process. So, what is the suboptimal algorithm? What does it look like? Well, we first perform hard decision decoding on the received symbol to form a received vector nu. So, the first vector nu, which is the received vector, is n bit long. We do not know whether nu is the valid code word or it is a code word plus error. So, the first job is to find that out. So, we find the S as nu H transpose. Okay, this is the syndrome decoding step, and I will jump with joy if S comes out to be 0, and I will declare new to be the correct valid code word. However, if S is non-zero, my fun begins and I will try to take a call based on a bit flipping algorithm. So, note that each component of new affects only S components of the syndrome S. Okay. If only a single bit is in error, only S syndrome components will be equal to 1. So, this is an important observation. So, now we compute all checksums and the number of unsatisfied parity checks involving each of the n bits of new are figured out. So, what we do is, if new is non-zero, I start my action and I try to identify which of the elements of new are leading to the unsatisfied parity checks. For those bits of new which are involved in the largest number of unsatisfied parity check, I flip them. This is the bit flipping algorithm. And then I go back to my step 3, which is again compute the checksum, and again go and see, flip those bits of new received vector which are involved in the largest number of unsatisfied parity checks, and I keep doing it till all the checks are satisfied, that I get a 0 vector in new prime H transpose, or the maximum number of iterations allowed are reached and I declare that sorry, I could not find the answer. So, this bit flipping algorithm does not guarantee that errors up to half the minimum distance are corrected. However, for large block lengths, this suboptimal algorithm works remarkably well. So, let us look at a very simple example. This is the rate 1 by 3 code. So, if you can see that this is n minus k and this is n. So, this n is 6, all right, and this is your parity check matrix. Here every column, if you see, has r is equal to 2, and if you observe every row, s is equal to 3 ones are there. So, for this, even though in the truest sense it is not a sparse matrix, but it will, at least it fits the slide, and we are not going to go for a much larger toy example here. So, n is equal to 6, r is equal to 3, s is equal to 2. Okay. But this is, we have said, this is not, n is not large enough to yield a really sparse H matrix, but we will live with it. So, we first construct the Tanner graph. What do we do with it? On the right you see that the H matrix is there. On the left I have put the Tanner graph, it is a bipartite graph. Here we have these nodes and this is the check nodes. Now, please note that 1 1 1 0 0 0. So, this C0 is connected only to S0, S1, S2. What do these relate to? These correspond to your new vector that you receive. The vector that you receive, yes, that is of the length n, block length, and if there are errors in S0, S1 and S2, they will relate to this C0. What is this? Well, this is my syndrome. So, the greens are my elements on the syndrome vector, reds are the elements of the received vector. Whenever you put the received vector new and process it through H transpose, you get these as the syndrome. So, what is the beauty is that because of the sparsity, there are very few connections actually. If I start increasing the number of ones in my parity check matrix, the number of interconnects would just go up. So, limiting, I can keep increasing my n, but I will limit the number of connections, and therein lies the beauty of this low density parity check. So, if my received vector leads to a syndrome which is 1 0 0 0, it clearly says that this guy which is 1 should flag and lead me to S0, S1, S2 being the culprits or the suspects. On the other hand, if I have 1 0 0 1, so this C3 also shows a 1, it means that S2, S4 and S5 which are connected to C3, one of them is possibly wrong. So, if I look at this guy, I have these two and so on and so forth. So, you know that whichever element becomes a 1, it has some suspects that it raises up, and I will do a voting and see which of the nodes are maximally under suspicion. So, let us understand this with a simple example. Suppose we happen to receive a vector 0 0 1 0 0 0 at the receiver, and I wish to know whether this is a valid code word, whether I have made an error. If yes, then what is the corrected version. So, first step is to find out the syndrome. I quickly take my H matrix and I perform nu H transpose and I get 1 0 0 1, which is a non-zero. So, clearly I declare that this received vector nu is not a valid code word. But then what is that code word which resulted in this error? I need to do the correct decoding. Let us do this bit flipping algorithm for this LDPC codes to do so. First observation is that the syndrome has the first element and the last element as ones and rest are zeros. Okay. 0 0 0 0 would say nobody has made any errors. These two might lead to which of these have made an error. So, this implies that there is an error among the symbols connected to the check nodes 1 and 4. These are the check nodes and 2 flags have gone up in the Tanner graph. So, we make the following observation. Okay. So, we pull up the Tanner graph and we look at the syndrome and we identify the C0, the first element of my syndrome, and the last C3. They are the ones whose flags have been raised. And now I have to go back and see which of these received vector, which of these elements need to be flipped or changed so that I can get a 0 0 0 0 here. That is the logic. So, first I look at this first guy. First one, it is only connected to these 3. So, first guess is that any one of these 3 S0, S1, S2 could have resulted in this one. Either this is flipped or this is flipped or this is flipped, but I do not know. So, I look at the second guy and I see, well, C3 is connected to S2, S4, S5, right. Now, S2 is raising the maximum suspicion, because not only is it connected to C0, but it is also connected to C3. So, what I do is I pull back my nu, the received vector, and I said, okay, which is that number 3 position? This is the guy which is connected to 2 of the check nodes which are in error. So, I flip it. It is a bit flipping algorithm. So, I am not sure whether it is right or not, I am taking a guess, it is an intermediary step. So, I flipped this. Having flipped this, I again perform this nu prime H transpose, but this time I will get a 0 0 0 vector. So, the syndrome will be 0. So, this bit flipping has led me to a correctly decoded vector nu, which is the all 0 vector that was sent. So, this is a simple example that tells me how a bit flipping algorithm works, and this is exactly what is written in this slide. So, bit 4 of the received vector corresponds to no failed checks, bit 1 and 2 of the received vector corresponds to check node 1, similarly bits 5 and 6 to check node 4. So, we follow this up and look at the conclusion that third bit could be possibly flipped. We do that flipping and check for the parity check matrix. Hence, the corrected vector is the all 0 vector in our case. Now, let us move a little bit ahead and we start defining an optimal code. So, what is an optimal code? An optimal n comma k comma d star code is such that none of it cannot be really improved. How can you improve it? Well, there are 3 parameters n, k, d star. N minus k represents the overhead. So, I can improve this n comma k comma d star code by ensuring that even if the d star is the same, k is the same, I can have less overhead. So, I can have n minus 1 comma k comma d star. So, if I can find a code which is n minus 1, so it is a shorter code, block length is reduced without changing the number of information word and it still gives me the same minimum distance, then I have improved upon the code. Or I said, look, d star I am not touching, I can increase n to n plus 1 and I increase k to k plus 1. So, what does it mean? That my code rate has become k plus 1 over n plus 1, and I can keep going and I make it k plus 2, n plus 2. So, you can improve the code rate, right, because that fraction goes closer to 1 by this. You agree that k plus 1 over n plus 1 is a closer to unity than k over n, like 1 by 2, 2 by 3, 3 by 4, so on and so forth. So, your code rate keeps improving without decreasing your d star. So, again you have an improvement. Or I said, look, I have n plus 1, I do not touch k, but that increase of 1 gives me d star plus 1, just as we did for that Hamming code, that we had a 7 comma 4 code and we added a parity and did d star become larger or not. So, if I can do so, if we have an n comma k comma d star code for which no such codes exist, then this is an optimal code. Okay. So, none of the nearest improvements hold water, such is an optimal code. For example, this 24 comma 12 comma 8 is a binary code which is optimal, because you can check that if you reduce this n, you can't find, you can disprove that 23 comma 12 comma 8 code, it does not exist, right. This 25 13, so you increase it, this code also does not exist because 24 plus 1 25, 12 plus 1 13 8, so this also does not exist, and this n plus 1 25 12 and d star is equal to 9, this code also does not exist. You can take your time, prove it anyway, either by construction or you can prove in terms of the violation of the singleton bound, whatever you want to do, and you can show that these codes do not exist, and therefore 24 comma 12 comma 8 is indeed an optimal code. Now, we come to one final definition, which is the maximum distance separable codes, which is the MDS code. How does this work? Well, we start from the redundancy. So, finally, we are trying to correct a certain number of errors by adding a certain number of redundancy. So, we say for a given redundancy r, therefore, my code is n comma n minus r. Okay. K is equal to n minus r, because the redundancy is r, we are adding r bits to k to make it n, but whose minimum distance is equal to r plus 1. So, by adding r redundancies, you are having a minimum distance r plus 1. Such a code is the MDS code. you can easily see that MDS codes meets the singleton bound by substituting this. Some important and interesting properties of MDS codes are that a QRE n comma k linear code is an MDS code if and only if the minimum non-zero weight of any code word is n minus k plus 1. There is one interesting property. And also a QRE n minus k linear code is an MDS code if and only if every set of n minus k columns of the parity check matrix is linearly independent. So, we can verify these two properties of MDS codes. So, these are, so we will see that binary MDS codes rarely exist, we will have to go to QRE codes for getting meaningful MDS codes. And when we talk about Reed-Solomon codes, we will find that they are indeed maximum distance separable codes. So, we come to the end of this lecture. Let us summarize what we have learnt today. We have covered Hamming codes, and then we looked at the interesting class of codes called low density parity check codes. We then defined what are optimal codes and MDS codes. We also looked at some examples. With that, we come to the end of this lecture.